Welcome to this lecture introducing artificial intelligence. In this lecture, we'll start by defining artificial intelligence and distinguishing it from other related terms. Next, we'll discuss the fundamental concepts upon which AI is built. Then we'll provide an overview of three key concept areas, including knowledge representation, logic, and reasoning. Let's start by defining and distinguishing artificial intelligence. For many years, when someone mentioned the term artificial intelligence, I think most people would immediately conjure mental images of robots and other artificial intelligence entities coming from science fiction, TV, and cinema. Much more recently, applications of AI in the form of generative tools and apps, as well as self-driving cars, have gained public visibility and started to shift public perceptions about what AI could be in their lives. With respect to generative AI, we already have access to a number of digital assistants, content creators, search engines, and large language models, as well as tools for coding and development, design and visual arts, and audio and video generation. For example, I used Nano Banana Pro in Google Gemini to create this visual representation of my new artificial intelligence course at the Cedars Sinai Medical Center in Los Angeles. The image generator created a pretty impressive degree of detail, specificity, and adherence to the information in my prompt. Now let's take a moment to look at some selected definitions of artificial intelligence, which is sometimes referred to as machine intelligence, or intelligence demonstrated by machines. Russell and Norvig describe artificial intelligence as machines or computers that mimic cognitive functions that humans associate with the human mind, such as learning and problem solving. In 1955, McCarthy defined it as machines that behave as though they were intelligent. Encyclopedia Britannica from 1991 defined it as the ability of digital computers or computer-controlled robots to solve problems that are normally associated with the higher intellectual processing capabilities of humans. Rich in 1983 defined it as the study of how to make computers do things at which, at the moment, people are better. Causey, in 1997, defined it as getting computers to do tasks that require human intelligence. And a recent inquiry to Google Gemini defined it as a field of computer science dedicated to creating systems capable of performing tasks that typically require human intelligence. It's important for you to distinguish the term artificial intelligence from machine learning early on, where the term artificial intelligence describes a field much broader than machine learning alone. Machine learning is defined as a subset of artificial intelligence in the field of computer science that often uses statistical techniques to give computers the ability to learn with data without being explicitly programmed. Here, an important element differentiating machine learning is its dependency on learning from data. Sticking with the subfield of machine learning for a moment, we can describe it as a strategy for discovering patterns or associations within data. And further, we want to represent those patterns as useful generalizations, for example, models. And this process of generalization involves looking at specific examples and simplifying them to some best fit representation. For example, let's say we have this set of specific cartoon trees, and you want to generalize them in some way to come up with a model of what it is to be a tree. Downstream, we can apply that generalization to decision making, in other words, for the task of classification or prediction. For example, we might try to classify these two specific cartoons as either a tree or not a tree based on our model. There are many possible approaches to machine learning that initially we can categorize by learning style. The first category is supervised learning, that involves learning on labeled data. This can include classification tasks seeking to predict membership in two or more classes or categories, or regression, seeking to predict a quantitative value. Another category is unsupervised learning, that involves learning on unlabeled data. This can include tasks such as clustering or dimensionality reduction. A somewhat newer category is semi-supervised learning, which aims to make the most of partially labeled data. And the last category is reinforcement learning, which focuses on online learning from an environment and typically focuses on complex multi-step problems, like learning to play multi-step games like chess. Now let's take a look at the term artificial intelligence as part of a hierarchy of terms. In this first diagram, we can again see machine learning as being a subset of the field of artificial intelligence. But further, we can see that the term deep learning describes a subfield within machine learning. Deep learning refers to methods such as multi-layer perceptrons, convolutional neural networks, and recurrent neural networks. Machine learning more broadly also includes methods such as k-means, k-nearest neighbors, support vector machines, and decision trees. And artificial intelligence even more broadly includes methods not falling under machine learning or deep learning, such as rule-based expert systems or closed-loop systems. In this second figure, we can also see that generative AI is a subfield of deep learning. Large language models are a subfield of generative AI, and ChatGPT is a specific large language model. In this Venn diagram, we can see how other fields and terms relate to artificial intelligence. For example, while artificial intelligence is primarily founded in the field of computer science, statistics is primarily founded in the field of mathematics. At the intersection of the two is the field of data science and data mining. Also, you can see terms such as cognitive computing and predictive analytics nestled within the realm of machine learning and artificial intelligence, but still overlapping with the field of statistics. There's also symbolic AI, which is a more traditional approach to artificial intelligence, robotics, and other specialized areas of machine learning and artificial intelligence, including computer vision, natural language processing, and generative AI. So why are people interested in artificial intelligence? There are many tasks which we might reasonably think require intelligence, for example, complex arithmetic, which is traditionally easy for computers. However, some tasks may seem easy for people, but have been traditionally very difficult to automate. For example, recognizing a face or interpreting text. Artificial intelligence is concerned with these difficult tasks, which require complex and sophisticated reasoning processes and knowledge. Overall, the promise of AI includes automation, focused on speed, efficiency, and the reduction of manual human effort; scale, focused on performing tasks at scale that most or all humans can't achieve; discovery and innovation, focused on integrating information to find novel patterns, designs, and strategies; and generation, of text, voice, video, images, code, and many other possibilities. When it comes to AI, simple automation can be enough to qualify. I think much of the time people are tempted to think of extremely advanced, complex, and sophisticated methods when it comes to what constitutes artificial intelligence. And while this certainly can be true, artificial intelligence automation could be as simple as a series of if-then loops in computer code specifying distinct actions in different situations. Here we take a look at a modern view of artificial intelligence, defined as computational methods that enhance, extend, and expand human intelligence capabilities. Artificial intelligence is the capacity of machines to memorize and learn from experience, to think and create, and to assist and augment decisions in real-world applications. This pyramid illustrates progressively more sophisticated capabilities of artificial intelligence, beginning with rule-based systems that can be explicitly programmed based on existing human experience or criteria. Then there's machine learning, which interprets data patterns and learns from it to develop new rules, alerts, automations, or predictions. The next level is prescriptive, with AI drawing conclusions from data and offering recommendations to optimize or prescribe a course of action. Beyond this is generative, with AI trained to recognize patterns in data and generate new content based on those patterns. And lastly, thus far least obtainable, is that of awareness, where AI understands intentions, simulates human relationships, and creates a sense of self as an expert. Now let's briefly tour areas of AI research and development, beginning with some traditional and foundational areas. These established fields remain crucial and form the backbone of modern AI systems. First, there's symbolic AI, also known as good old-fashioned AI, focusing on using human-readable symbols and explicit rule-based systems to represent knowledge and logical reasoning. These include expert systems, which mimic the decision-making ability of human experts within a specific domain, relying on a large rule base developed through symbolic AI principles. Then there's machine learning, the foundational methodology where computers learn patterns from data. Research continues into the refining of such algorithms for various tasks like classification and regression, with particular interest in deep learning and large language models, as well as model interpretability, explainability, and fairness bias mitigation. There's also predictive analytics, which uses statistical models and machine learning to forecast future outcomes and trends based on historical data. Other traditional and foundational areas of AI research and development include natural language processing, which enables computers to understand, interpret, and generate human language. It's a critical component of modern systems like search engines and chatbots. There's also computer vision, which gives machines the ability to see and interpret the visual world from digital images and videos used widely in medical imaging and autonomous vehicles. Also, planning and optimization, which involves developing algorithms that can devise sequences of actions to achieve a goal efficiently, a core component of logistics and robotics. There's also voice-to-text and text-to-voice, involving specialized natural language processing applications focusing on speech recognition and synthesis, powering virtual assistants and accessibility tools. And robotics, which integrates AI with mechanical engineering to create machines capable of performing physical tasks in the real world, from manufacturing to surgical assistance. Now we'll discuss some modern and emerging frontiers of artificial intelligence research and development. These cutting-edge areas represent where significant innovation and investment are currently concentrated. The first is generative AI, or Gen AI. This is a rapidly growing field focused on creating new original content, such as realistic images, sophisticated text, music, and code, using models like general adversarial networks and transformers. Also, automated machine learning, seeking to automate the end-to-end process of building and deploying AI models. And multimodal fusion, where models are being designed to process and synthesize data across diverse formats, including text, image, audio, and video simultaneously. This allows for deeper contextual awareness, such as an AI seeing a web page and discussing its content with a user. Also, agentic AI and autonomous systems. This research frontier is shifting from passive chatbots to autonomous agents. These systems can independently reason through multi-step tasks, use external tools, and adapt to changing environments without constant human prompting. There's also neurosymbolic and explainable AI, aimed at improving trust. This research is integrating symbolic reasoning, which excels at applying clear logic, with neural networks, which excel at pattern recognition. The goal is to move away from strictly black box models towards systems that can clearly explain the reasoning behind their decisions. Also, AI for science, which is about utilizing AI methodologies to accelerate the pace of scientific discovery, particularly in fields like material science, drug discovery, and climate modeling. Such AI co-scientist systems are being developed to uncover original knowledge rather than just summarizing existing literature. And quantum machine learning, which is an emerging research area exploring using quantum computing to handle complex optimization and faster data representation, specifically for drug discovery and financial modeling. Many, if not all of these areas of artificial intelligence research and development have or may be applied to biomedicine. There are many application opportunities targeting different clinical outcomes, data types, unique challenges, and improving human experience. To date, there's been a particular focus on machine learning and predictive modeling, computer vision, including segmentation and diagnosis, natural language processing, and chatbots or generative AI text. Now we'll move on to providing an overview of fundamental concepts in AI. Here we've laid out some of the key fundamental concepts which underpin artificial intelligence methods and applications. These include knowledge representation, reasoning, logic and inference, handling uncertainty, search and optimization, ethics, data literacy, learning, perception, and planning. In this lecture series, we'll be focusing more on the concepts towards the top of the list, with less focus on learning, since we leave this to other machine learning courses, as well as less attention being paid to perception and planning, despite all of these being important to the field as a whole. From a big picture perspective, one of the hallmarks of intelligence is the ability to reason. Reasoning allows us to solve problems. And if we want to build intelligent machines, we must be able to automate reasoning. Logic is the study of how we correctly reason. And two of the primary goals of logic are to represent knowledge of the world and to reason with that knowledge. But what is knowledge? The very definition of knowledge is an ongoing debate among philosophers. For our purposes, let's define knowledge as statements such as facts, information, or descriptions that are regarded as true or correct, or at least highly probable of being true. As a very simple example, some knowledge might include the statement that a dime is better than a nickel, and a nickel is better than a penny. Such knowledge is acquired through experience or education through perceiving, discovering, or learning. This may seem simple, but what about communicating knowledge, or manipulating existing knowledge to draw conclusions to be able to derive new knowledge? This brings us to the term inference, which is defined as a conclusion reached on the basis of evidence and reasoning. One type of inference you may already be familiar with is that of statistical inference, where we can take a sample from the larger population from which we tried to draw conclusions based on that sample that will later successfully generalize back to the whole population. Consider the tale of three blind men and the elephant. The first touches the trunk, and with this evidence, he believes he's touching a snake. The second touches its side and concludes they're touching a wall. And the third grabs its tail and thinks he's holding a piece of rope. This helps to illustrate how important it is to have sufficient evidence and rules for reasoning to be able to reach valid conclusions. Now let's define reasoning, which is the drawing of conclusions or inferences from known or assumed knowledge. Consider the following. We have the knowledge that a dime is better than a nickel, and a nickel is better than a penny. From this, we can apply reasoning to conclude that a dime is better than a penny. There are many ways to reason, and the example we just gave is one that involves logical deductive reasoning, or more specifically, a syllogism. In this schematic, we look ahead to how some of these pillars of AI play a central role in AI systems. Note how knowledge representation and reasoning are at the core of almost everything that we consider to be AI. Now let's look at the basics of knowledge representation. First off, what is knowledge representation and why does it matter? Knowledge representation is the subfield of artificial intelligence dedicated to transforming information from the real world into a specialized and/or structured digital format that a machine can use in order to perform complex tasks, such as reasoning, learning, problem-solving, and mutual understanding. Knowledge representation is important to reasoning in that it enables artificial intelligence to draw new conclusions from existing knowledge. It's important to learning because it provides structure for machines to acquire new knowledge. It's important to problem-solving in general because it allows AI to apply structured information to solve complex tasks. And it's important to understanding in that it bridges the gap between human concepts and machine processing. Over the next few slides, we'll take a look at some different types of knowledge. First, there's declarative knowledge, which we can think of as the what in knowledge. This includes facts, concepts, and descriptive information about the world. It is static and typically stored as statements of truth. Examples might include, Paris is the capital of France, or a parrot is a type of bird. This type of knowledge would be used for powering knowledge bases and expert systems, where logic is applied to stored facts in order to infer new insights. Structural knowledge is another type. This captures relationships and connections between different concepts or objects. It provides the framework for problem solving by organizing information into hierarchies or networks. Examples might include knowing that a dog is a mammal and a poodle is a dog, which defines a hierarchical structure. Use cases might include mapping relationships in knowledge graphs or semantic networks. Procedural knowledge is another, which gets at the how and is also referred to as imperative knowledge. This is about understanding how to perform specific tasks or actions. It is dynamic and focused on sequences of rules, steps, or algorithms. For example, the steps to solve a quadratic equation, bake a cake, or drive a car. Such knowledge might be essential in robotics for navigation and industrial automation. Then there's meta-knowledge, or knowledge about knowledge. This seeks to capture a higher-order understanding, such as knowing what information is available, how reliable it is, and when to apply it. One example might be a medical AI system determining whether advice comes from a trusted scientific journal or instead from an unverified blog post. Such knowledge can be critical for self-correction, filtering misinformation, and optimizing learning strategies in advanced models. Also, there's heuristic knowledge, or experience-based knowledge. This includes rules of thumb, or what could be referred to as shallow knowledge. Here, heuristics represent basic best practices or expert intuition gained from past experiences. It allows artificial intelligence to make quick decisions when complete information is unavailable. One example from the game of chess is that it's usually beneficial to control the center of the board. And a use case might be in artificial intelligence game playing, AI, and complex search algorithms like the A-star search, used to find efficient approximations rather than perfect solutions. Some other specialized knowledge types might include temporal and spatial knowledge, representing information about time, physical space, and movement, which might be crucial for autonomous vehicles. Common sense knowledge, including fundamental obvious facts that humans acquire naturally, such as water is wet, which are notoriously difficult for artificial intelligence systems to formalize. And domain-specific knowledge, including highly detailed information restricted to specialized fields like law, finance, or molecular biology. One key challenge is how to communicate knowledge with a machine. When we go to transfer human knowledge into a machine, this often leads to what's known as the knowledge engineering bottleneck, which remains a central hurdle in AI research. Some primary challenges in this communication include the following: tacit knowledge and intuition. Much of what humans know includes skills or insights that are difficult to explain in words or rules. For example, how to balance on a bike, or how a doctor intuits a rare diagnosis. Because humans cannot always verbalize these internal heuristics, they can't easily program them into an AI. Common sense and the frame problem. Humans possess a vast background of obvious facts that we don't always think to mention. For example, if you move a cup, the coffee inside moves with it. Machines, on the other hand, traditionally lack this innate understanding. The frame problem refers to the difficulty of telling a machine everything that doesn't change when an action is performed, leading to logical gaps in AI reasoning. Another knowledge communication challenge includes knowledge mismatch or formalization. Human knowledge is often fuzzy or probabilistic, whereas traditional computer systems require formal binary logic. Translating a nuanced human opinion into a rigid knowledge representation, such as an ontology or set of rules, often leads to a loss of meaning or an oversimplification. Also, we have the grounding problem. Humans understand symbols because they're grounded in physical reality. For example, we know what red looks like and what hot feels like. Machines often deal with ungrounded symbols. In other words, they may know the definition of the word fire without understanding its physical properties, dangers, or utility. Bias and subjectivity. When humans communicate knowledge, they inadvertently pass on their own cognitive biases, cultural assumptions, and errors. If an AI is built on this polluted knowledge transfer, it can replicate and scale those human failings, making the system unfair or inaccurate. And the last knowledge communication challenge we'll mention is that of linguistic ambiguity and context. Human language is inherently imprecise and relies heavily on context, tone, and shared culture. One example of this is called polysemy, where a single word like bank can mean a financial institution or a river's edge. Another example involves pragmatics, where a person saying "it's cold in here" could be an indirect request for someone to close a window, whereas an AI might interpret it only as a temperature report. Here's another specific example where we have two statements of knowledge, including a penny is better than nothing, and nothing is better than world peace. While at first glance, it seems that perhaps we could conclude that a penny is better than world peace, clearly this statement is invalid. Ultimately, natural language is tricky and often ambiguous, and in practice, often an impractically huge knowledge base may be needed to understand context. Therefore, we need a more consistent, controlled way to represent knowledge in order to ensure that our conclusions are valid and that a computing system can make effective use of knowledge. Now let's discuss moving towards formal representations of knowledge. As we've implied, solving problems in a particular domain will often require knowledge of objects and how to reason with that knowledge. A formal representation standardizes objects and reasoning. However, to get there, we need to be able to map information from a natural to formal format. Of note, a natural downside of this is that we often lose flexibility in this mapping. In 1993, Ginsburg stated, "The intended role of knowledge representation in AI is to reduce problems of intelligent action to search problems." Let's take a look at this process of mapping between natural language and formal language. We start with some initial facts that we currently possess in the context of natural language on the left. We can then use mappings based on semantics to create a formal representation of those facts. Now we can apply formal reasoning to derive formally represented conclusions. And lastly, we can use mappings based on semantics to recreate these conclusions back in natural language. Thinking about formal representations, we know that knowledge will need to be represented effectively, consistently, and in a meaningful way. Symbol structures allow us to represent bits of knowledge. For example, the word blue can be used to denote a particular color, and the symbol structure blue parenthesis Monica car might be used formally to denote the fact that Monica's car is blue. In the early days of AI, symbol structures could be represented using any physical medium, such as punch cards. Today, computers make this a lot easier by means of programming languages. Facts can now be stored in data structures like lists, dictionaries, arrays, and data frames, and reasoning can be achieved using digital programming code rather than any mechanical systems. So what are the desirable properties of a knowledge representation? One would be representational adequacy. In other words, can it represent all knowledge you need to reason within a particular field or domain? Another would be inferential adequacy. In other words, does it allow new knowledge to be inferred from a basic set of facts that constitute your present knowledge? One thing to look out for here is to avoid representations that might require you to enumerate negative statements or facts that could instead be covered by a single positive one. Yet another would be inferential efficiency, where inferences from reasoning should be able to be made quickly, easily, and with computational tractability. Also, acquisitional efficiency. Does the representation allow us the ability to gain new knowledge automatically, helping the AI to add to its current knowledge, and consequently becoming increasingly smarter and productive? Also, clear syntax and semantics. In other words, does the representation know allowable expressions of the language and what they mean? And lastly, naturalness. Is the representation reasonably natural and easy for human beings to work with? Let's take a moment to more closely examine the terms syntax and semantics. Syntax is defined as the form, grammar, or structure of expressions, statements, and program units, or in other words, allowable expressions. Semantics, on the other hand, is the meaning of the expressions, statements, and program units. So, in defining syntax, an example might be that blue parentheses Monica dash car is okay. It's allowed. But the representation Monica dash car parentheses blue and black is not structurally okay. An example of semantics might include that the symbol structure blue parentheses Monica dash car means Monica's car is blue, but it does not mean an instruction to paint Monica's car blue. This distinction is obviously very important for drawing new conclusions. Also, let's talk a bit more about the naturalness of a knowledge representation. it's often useful to choose simple structures that are meaningful to the human being working with them. Consider the natural language fact that if someone has a headache, they should take aspirin. One possible representation might be if parentheses x, h, a, where x is someone, h is a headache, and a is aspirin. While this is certainly compact and efficient, it might be more difficult for a human being to work with in practice than some alternatives. For example, in representation 2, we capture the same statement with the simple structure if symptom, parentheses x, headache, then medication, x, aspirin. Both of these representations could be a formal language interpretation of the natural language statement in green. However, the latter of the two is arguably more readable and easier for human beings to deal with depending on the use case. Next, on this slide, we'll identify many of the common knowledge representation strategies used in the field of artificial intelligence. This first grouping of traditional and logical strategies tend to focus on human-readable expressions and the application of formal mathematical logic. These include logical representation, production rules, semantic networks, and frame representations. Our second group of representation strategies are structured and contextual. These focus on the flow of events, as well as deep, domain-specific relationships. And these include ontologies, case-based representations, scripts, and procedural knowledge. And our last group include probabilistic and modern strategies, which tend to be the engines of modern AI that can handle uncertainty and massive datasets. These include probabilistic graph models, distributed or vector representations, and neural symbolic representations. For the remaining slides in this section, we'll define each of these representations further, as well as provide brief examples and use cases. First, we have logical representations. These use formal mathematical logics, such as propositional or predicate logic, to represent facts and rules to ensure precise inferences. An example of this might be if X is a bird and all birds have feathers, then X has feathers. Such representations might be used in legal AI systems meant to check contracts for compliance with strict statutory laws. Second, we have production rules. These encapsulate knowledge in a series of if condition, then action statements. For example, if fever and cough, then consider flu. These representations are a common part of expert systems, which can be used as medical diagnostic tools that follow established clinical protocols. Third, we have semantic networks. These are graphical models with nodes as concepts and links capturing relationships to show how things connect. For example, the concept of a bird is an animal. A use case might be in web search, for example, powering Google's knowledge graph to show people who ask results. Fourth, we have frame representations, which are data structures for representing stereotypical situations with slots for attributes. For example, we could have a hotel room frame with slots for bed being king-sized, price being $200, and Wi-Fi being a yes. Such representations might be used in e-commerce, for example, in standardizing product specifications for comparison engines. Fifth, we have ontologies, which are a formal shared vocabulary of concepts and their complex interdependencies. This could be, for example, a mapping of every gene, protein, and drug interaction in a specific disease medical ontology. This might be used in drug discovery to accelerate the identification of new treatment targets. Sixth, we have case-based reasoning, which represents knowledge as a library of past experiences rather than general rules. One example might be using 10,000 past structural failures to predict if a new bridge design is safe. One use case might be in customer support to create automated troubleshooting based on what worked before. Seventh, we have scripts, which are a chronological playbook of actions expected in a specific social context. For example, the steps of an ATM transaction, where we insert card, enter PIN, and select amount. One use case might be in service robotics, to help robots navigate social norms in hotels or hospitals. Eighth, we have procedural knowledge, which stores knowledge as procedures or algorithms such as recipes to perform tasks, for example, how to play chess. One use case might be in automated surgical robotics. Ninth, we have probabilistic graphical models, or PGMs, which use Bayesian logic to represent knowledge as a set of conditional likelihoods. These systems model how the likelihood of one event depends on another, allowing the AI to reason under uncertainty. For example, given that it's cloudy 80% of the time, there's a 60% chance it will rain within 2 hours. A possible use case for these might include clinical decision support tools or personalized oncology. 10th, we have distributed vector representations, which encode knowledge as numerical patterns or embeddings in a high-dimensional space. One way they do this is encode knowledge as patterns and weights between interconnected nodes while learning from data. This approach is dominant, for example, in neural networks and deep learning. An example of this representation is that the word king may be mathematically positioned near the words queen and royalty in a problem space. Use cases here include machine learning, modeling, and generative AI. And lastly, we have neurosymbolic representations, which are hybrid strategies that merge logical rules with neural network pattern recognition. For example, using a neural network to see a stop sign combined with a logical rule to know that the word stop always means halt. Use cases here include automated finance compliance and anti-money laundering, where the goal is to detect incredibly subtle evolving patterns of fraud, which requires the intuition of neural networks, while strictly adhering to rigid legal regulations that require a transparent audit trail, which in turn requires the logic of symbolic AI. Now we move on to the basics of logic. Overall, the goals of logic include representing knowledge of the world and reasoning with that knowledge. Logic is arguably the most important approach to knowledge representation, at least historically. A logic, almost by definition, has a well-defined syntax and semantics, and is concerned with truth-preserving inference. Logic studies the ways in which humans reason formally through argument. And the term logic usually refers to either propositional logic or first-order predicate logic, both of which we'll cover in other lectures. Let's start by defining a logical argument. This is a finite set of statements consisting of premises, in other words, facts, knowledge, or supporting evidence, and a conclusion. A logical argument puts reasoning into words, and a conclusion is typically identified by a therefore symbol, given by these 3 dots. An example of a logical argument might look like this, where we have 2 premises and a conclusion. This logical argument states that if you overslept, you'll be late, you aren't late, therefore you didn't oversleep. But how do we describe the quality of an argument? One way to do this is by distinguishing valid from invalid arguments. Valid arguments have a correct logical structure, or the conclusion must be true if the premises are true, regardless of whether the premises are actually true in real life. Validity is critically all about form or structure of the argument, and not the real-world truth of the statements themselves. A necessity of a valid argument is that it's impossible to have the premises all be true and yet the conclusion still be false. Now let's look at a few examples and distinguish whether they're valid or invalid. This first example argument states if you overslept, you'll be late, you aren't late, therefore you didn't oversleep. This argument is valid because if we assume the first 2 premises are true, then it follows that the conclusion is also true. The second example starts the same, saying if you overslept you'll be late. However, the rest of the argument states that you didn't oversleep, therefore you aren't late. This argument is invalid because when you think about it, there are other ways for you to have possibly been late other than oversleeping. Just because you didn't oversleep doesn't mean you necessarily were on time. Our third example says if you're in France, you're in Europe. You aren't in Europe, therefore you aren't in France. This again is an example of a valid argument. The last example again starts the same, but then says you aren't in France, therefore you aren't in Europe. This argument is also invalid for similar reasons to the argument above it. A second way to express the quality of an argument is to indicate whether it is sound or not. A sound argument is a valid argument where all of the argument's premises are also actually true in real life. Such arguments both have a perfect form as well as have factual accuracy. Therefore, an argument can be unsound in two ways. Either it has a false premise, or a conclusion might not follow from its premises. Our first example argument states that if you're reading this, you aren't illiterate. You're reading this, therefore you aren't illiterate. This argument is both valid and sound. Our second example states that all logicians are millionaires. Jen is a logician, therefore Jen is a millionaire. While the structure of this argument makes it valid, the premise, all logicians are millionaires, is sadly provably inaccurate. Therefore, this argument overall is valid but unsound. And our third example states that all millionaires eat well. Sam eats well, therefore Sam is a millionaire. This argument is both invalid and unsound, because it both has the false premise, all millionaires eat well, and it has a conclusion that does not follow structurally from its premises. Now let's introduce syllogistic logic, which was invented by Aristotle. Syllogistic logic typically uses syllogistic language, where we use capital letters for general categories of information and lowercase letters for specific items or individuals. Here we show an example of an argument in natural language being converted into the symbol structures of syllogistic language. Here, a big L is used to replace logicians as a general category, and S for smart, also a general category, and Jen is replaced by lowercase u, indicating a specific individual or case. Syllogistic logic relies on something called well-formed formulas, which rely on the syntax, or acceptable objects, of logic, specifically using 5 words: all, no, some, is, and not. Well-formed formulas have any of the following 8 forms. All A is B, some A is B, X is A, X is Y, no A is B, some A is not B, X is not A, and X is not Y. Make note of the use of capital and lowercase letters in these examples. These 8 forms capture the various valid ways that our 5 syntax connectors can relate general and specific objects. We can use Venn diagrams to help us visualize some well-formed formulas. A Venn diagram is simply a diagram consisting of various overlapping figures contained in a rectangle that represent the universe U. In our first example well-formed formula, we have all A is B, which can also be interpreted as if A, then B. We can see this visually represented such that anything that is A is also part of B, but the opposite is not true. And our second example, we have no A is B, which in our Venn diagram means that A and B are completely separate. And our last example states some A is B, which we see visually represented as the circles A and B partially overlapping. This brings us to the syllogism, which are arguments that include 2 or more well-formed formulas in which each letter occurs twice, and the letters together form a chain. We can see an example of this here, similar to the arguments we've seen previously. We have 2 premises, which we refer to here as the major and minor premises, followed by a conclusion. We can see that the letter capital L occurs twice, forming part of a chain. And this is also true for the letters lowercase u and capital S. We can visualize here how if we connect these letters between the elements of the argument, that they collectively form a chain, where each well-formed formula has at least one letter in common with the well-formed formula just below it, and the first well-formed formula has at least one letter in common with the last well-formed formula. Together, this forms an argument that is similar to the transitive property in mathematics, where if A equals B and B equals C, then we can conclude that A equals C. One nifty logical tool is referred to as the star test, which is a simple visual method for testing a syllogism as a type of argument for validity. This starts by identifying any distributed letters in the argument, which we show underlined on the right in our well-formed formulas. A distributed letter is any letter that comes after a no or not, as well as the first letter after all, but not the second. The second step of the test is to put a star in front of premise letters that are distributed and any conclusion letters that aren't. We can see this here in an example valid syllogism, where we've put a star in front of the first L and the last S. Using this test, we can conclude that a syllogism is valid if every capital letter is starred exactly once, and there's exactly one star on the right-hand side of any line in the argument. This second example gives an invalid argument, where we can see that the capital letter A is starred twice, and there are two letters on the right-hand side, A and B, that have a star. And this last example, which is also valid, can be seen to also follow the rules of the star test. One last definition from logic that we'll introduce is that of an enthymeme, which is an argument in which the major premise is left unstated, but the conclusion is still supported by a single premise, because an unstated major premise is implied. As an example, we have the statement, "She must be a good student since she's on the dean's list." Breaking this down, we start with the conclusion, "She must be a good student," and have only included the minor premise, "She is on the dean's list." The implied major premise in this situation is that all students on the dean's list are good. Lastly, we move on to an overview of reasoning. In this lecture, we're going to cover 4 different types of reasoning: deductive, inductive, abductive, and analogical. Most artificial intelligence research and development to date has focused on utilizing deductive and inductive reasoning. In brief, for deductive reasoning, the goal is to apply general principles to reach a specific and certain conclusion. We can think of this type of reasoning as one that starts with a theory, forms a hypothesis, and then uses observations to confirm a conclusion. Inductive reasoning, on the other hand, seeks to derive general principles from specific observations. Here we start with observations and use them to look for a pattern, and we can apply this pattern to draw a probabilistic conclusion or hypothesis that can be applied as a theory to be tested. Abductive reasoning seeks to find the best explanation for incomplete evidence. Here we begin with incomplete observations, then derive assumptions or inferences, forming a hypothesis and leading to a best guess that again is probabilistic at best. And lastly, analogical reasoning aims to draw comparisons between similar specific cases or observations. Again here, we begin with specific observations, look for similarities between them, and then use this to suggest a possible hypothesis. Looking more closely at deductive reasoning, this starts with a general rule or premise and applies it to a specific case. If the premises are true and the logic is valid, it provides absolute certainty that the conclusion is known. This is also known as top-down reasoning. The logical flow here begins with general rules, leading to a specific case, upon which we make a certain conclusion. A conclusion here is reached reductively, applying general rules which hold over the entirety of a closed domain, narrowing the range under consideration until only the conclusion is left. Syllogisms are a common form of deductive reasoning from logic. One medically relevant example of deductive reasoning may start with the general rule that all patients with a specific mutation are allergic to penicillin. Given the specific case that a patient A has this mutation, we can conclude that patient A is allergic to penicillin. Typical AI uses of deductive reasoning include expert systems and other rule-based software where safety and strict logic, as well as certainty in conclusions, are paramount. On the other hand, inductive reasoning looks at specific observations and identifies a pattern to create a general rule. Here, the conclusion made is at best probable but never guaranteed. This is also known as bottom-up reasoning. A summary of logical flow here starts with specific observations, leading to pattern recognition, and finally the generation of a general probable rule or model. This strategy reasons from evidence about some members of a group in order to form a conclusion about all members of a group, like statistical inferences we mentioned earlier. Here, a conclusion derived through inductive reasoning is called a hypothesis, which is always less certain than the evidence itself. Of note, inductive reasoning here is not the same as induction in mathematical proofs. Mathematical induction is actually a form of deductive reasoning. A medical example of inductive reasoning might include the observation that in a study of 10,000 people, 95% of those with biomarker X responded well to drug Y. Here, the conclusion or hypothesis is that people with biomarker X generally respond well to drug Y. With respect to AI, inductive reasoning is the foundation of machine learning, which uses a set of specific instances to find useful generalizations. A statistical syllogism is a form of inductive reasoning, where you apply a generalization about a group or a reference class to a specific individual. This is also known as a proportional syllogism or a direct inference. Here we must concern ourselves with the correctness of the premise and conclusion link. This is analogous to the concepts of a valid or invalid argument. However, here we ask whether the correctness of the link between the premise and conclusion is either strong or weak. We also consider the truth of the premises as being either cogent or uncogent, or in other words, reliable or unreliable. This is analogous to a premise being true or false in logic. Here's an example of a statistical syllogism. 90% of Appalachian Trail shelters have water. The Rocky Gap is an Appalachian Trail shelter. Therefore, it's 90% probable that Rocky Gap has water. Note that while the statistical syllogism looks like the deductive reasoning argument structures we've seen so far in logic, it's a form of inductive reasoning since it deals with a proportion rather than a universal rule, leading to a conclusion that at best can only be probable. This slide gives an overview of the terms we've introduced describing the quality of reasoning arguments, both from a deductive and inductive reasoning perspective. Towards the top, we have valid and invalid, as well as sound and unsound arguments for deductive reasoning. And towards the bottom, we have strong versus weak and cogent versus uncogent arguments for inductive reasoning. To further highlight the difference between deduction and induction, we can draw a parallel to the concept of populations and samples common in biostatistical analysis. We can imagine that if we knew everything about a population, we could deduce certain conclusions about specific examples. Of course, this is usually not possible. We're forced to take a sample and apply induction to form a general hypothesis about members of a population. We can also talk about these terms in the context of learning or instruction, where deductive learning has a teacher presenting a generalization or rule to their students, and these learners will apply this general rule to specific examples or situations. This is different from inductive learning, where learners go about detecting or noticing patterns and working out a rule for themselves. Now let's move on to abductive reasoning, which starts with an incomplete set of observations and seeks the likeliest explanation. This could be thought of as the reasoning of detectives and doctors, or in other words, the inference of the best explanation. The logical flow here begins with specific observations, leading to the formation of possible hypotheses and the selection of a best fit explanation. Again, overall, this starts with an observation or set of observations and seeks to find the simplest and most likely explanation for the observations. A medical example of this might be to start with the observation that a patient has a high fever, a stiff neck, and a headache. We then consider the possible hypotheses of the patient having the flu, meningitis, or stress. And ultimately, given the severity, we conclude that meningitis is the most plausible and critical explanation to investigate first, even though obviously we don't have any certainty. Within AI, we find this type of reasoning in diagnostic systems, as well as troubleshooting systems where the data is noisy or can have missingness. And lastly, we look at analogical reasoning, which assumes that if two things are alike in some known ways, they're probably alike in other unknown ways. This is basically a comparison based on similarities. The logical flow here begins again with specific observations, then looking for similarities between those observations, and using these similarities to form possible hypotheses. As a medical example, we might speculate that this newly observed virus has a similar protein structure to the flu. Therefore, we might suspect flu antivirals might inhibit it. Within AI, this type of reasoning is used in case-based reasoning systems that look for similar past patients to suggest a treatment plan for new ones. To summarize this lecture, artificial intelligence is a broad term summarizing and overlapping a number of fields, including machine learning. AI encompasses a wide variety of methodological and applied research areas. Key fundamental concepts underlying all of AI include knowledge representation, reasoning, logic, uncertainty, search, and optimization. A wide variety of knowledge representation strategies have been proposed with different trade-offs which are suited to different goals and problem types. Logic offers well-established strategies to represent and reason with knowledge in order to yield certain conclusions. And there are multiple approaches to reasoning, including deductive, inductive, abductive, and analogical. I'm Ryan Urbanowitz, and thanks for joining me for this lecture. Stay skeptical, curious, and creative.